Hi students. For this first video for chapter 8, we are now going to delve into stoichiometry, but first we must have a review of the unit, the mole. So what is the mole? Well, it is a religious meeting of burrowing mammals. No, actually, what the mole is the number of elementary particles in a given quantity. So now we need to talk about its mass. So the molar mass is the mass of 1 mole. Remember that's 6.022 times 10 to the 23rd of something. That could be eggs, that could be shoes, that could be marbles, but we prefer to have atoms. Remember, as our particles get smaller, our units must get bigger. So we ended up devising this unit. 1 mole of carbon-12 atoms. Remember that being 6.022 times 10 to the 23rd atoms of carbon-12 weigh 12 grams. Notice that when we are using the mole, we use the gram. However, if we are going to talk about individual atoms or molecules, we are going to use the atomic mass unit. So 1 carbon-12 atom still has the same numeric mass, but we are going to change the unit. In this case, it will be 12 AMUs. So 1 mole of carbon-12 atoms is 12 grams. 1 mole of lithium atoms, if we go to the periodic table, has a mass of 6.941 grams of lithium. So for any element, the atomic mass unit and the molar mass are equivalent by number. This is why the periodic table does not have any units. So if we are going to ask for the mass of 1 or 2 or a small number of particles, we are going to utilize the AMU. If we are talking about moles, then we are going to use the units grams per mole. The math will be the same, but you must be comfortable using both units because we will deal with this both big and small. So now we need to figure out the conversion factor between the two mass units. So if it says we have 1 carbon-12 atom, and that's 12 AMUs, we can go and say that 1 mole of those atoms, which is 6.022 times 10 to the 23rd carbon-12 atoms, is 12 grams. We will actually get the unit of 1.66 times 10 to the minus 24th grams per AMU. So now you can see that the gram and the AMU are not equivalent, but because of our unit conversion, we are able to deem the numerics equivalent using our different Massius units. So as you can see here, we are going to cancel out our atoms and atoms. And we can say that 1 AMU is equal to 1.66 times 10 to the minus 24th gram, or actually a better way of looking at this is 1 gram, which is our SI standard unit, even though it's supposed to be kilograms, is actually a mole of AMUs. This is much easier to understand. So as we are going to go through a lot of math in this video, if we have the mass of the element, we can get to the number of moles of that element very easily by converting using our molar mass. Then, if we want to go from our number of moles of an element to, say, the number of atoms, then we must go and use Avogadro's number. So as you can see here, you must be proficient in going both directions. That means from going from our number of moles of an element to mass of an element. Maybe that means going from number of atoms of an element to number of moles, or vice versa. You must be able to do this math, and the best way of doing it is using your unit conversion. So remember that big M in this case is going to be our molar mass. Sometimes this is also known as the molecular weight, or you can see other vernaculars for it, but you will typically see this as a large M. And A, once again, remember, is Avogadro's number, which you know as 6.022 times 10 to the 23rd. So let's try a few examples of this math. Sulfur is a non-metallic element that is present in coal. When coal burns, sulfur is converted to sulfur dioxide and eventually to sulfuric acid, and that gives us acid rain. How many atoms are in 16.3 grams of sulfur? So what we need to do is start with our 16.3 grams. So if we have our 16.3 grams of sulfur, the next place that we need to go is to moles. So what we are going to do is say that we have 1 mole of our sulfur is going to be over the molar mass of our sulfur, which is going to be 32.01 grams of sulfur. So now we've gotten to moles, but that's not what we're asking for. We need to go to atoms. So if we are going to do that, we now need to have our Avogadro's number, 6.022 times 10 to the 23rd atoms of our sulfur over 1 mole of our sulfur. If we go and do our unit cancellation of getting rid of grams and grams and moles, notice that I have atoms of sulfur, which is what I want, and you will come up with a value of 3.07 times 10 to the 23rd atoms of sulfur. So as you can see here, by having approximately very close to half a mole of sulfur, I expect an answer that should be half a mole of atoms, which if it's 6.022 times 10 to the 23rd, getting an answer of 3.07 is fairly close. So now let's go ahead and calculate some molecular masses. First thing you want to notice is that I would like the answers in AMUs. This means that I am going to calculate the mass for one of these molecules. We are not wanting a mole. We are not going to be using grams, but in this case, we want to use the number and have it with the AMU. So let us look first at sulfur dioxide, which is SO2. So in this case, I am going to have 1 sulfur at 32.01 AMUs. And then I'm also going to have 2 oxygens. So in this case, I am going to add 2 times 16 AMUs, and I should get my answer, which I will get a molecular mass for this compound of 64.01 AMUs. If I had a mole of this compound, I could then say that I have 64.01 grams per mole, but I specifically asked for the molecular mass. Let's go ahead and take a look at caffeine. This is a compound that most of you rely on to get through your day because of it being a stimulant. So notice that I have to go and get many masses of many atoms, but it is the aggregate sum. So I am going to get 8 carbons, which is 12.01 AMUs. Then I will add that to 10 hydrogens, which is 1.008 AMUs. Then I will get 4 nitrogens, which is 4 times our 14.01 AMUs. And then finally, our last one, we are going to get 2 oxygens with a mass of 16 AMUs individually. If I put all of this into the calculator, you will come to find out that caffeine has a mass of 194.2 AMUs per molecule. So it's really important that you understand how to do this basic addition, because this is a skill you are going to use over and over, especially as we go into our further stoichiometry. Our third example is now going to talk about elementary parts. How many hydrogen atoms are present in 25.6 grams of urea, which I give its molecular formula, which is used as a fertilizer, an animal feed, and able to manufacture polymers. The molar mass of urea is 60.06 grams. So what we need to do in here is start with our 25.6 grams of urea. Well, now what we need to do is go to moles of urea. So what we can state is that 1 mole of our urea, and we want to put our molar mass on the bottom, so that is going to be 60.06 grams, and that gives us moles of urea. But moles of urea is not what we want. We want moles of hydrogen next. Notice that in each one of our ureas, we are going to have 2 amine groups. In each amine group, we have 2 hydrogens. So this means that we are going to get 4 hydrogens for each one of these compounds. So what I then need to do is come up with a ratio describing that. I will get 4 moles of hydrogen for every 1 mole of my urea. So now I've gotten to moles of hydrogen. So what do I want to do now that I would like to get to atoms of hydrogen? Well, that's very easy, and that is going to be us using our Avogadro's number, which is going to be our 6.022 times 10 to the 23rd atoms of hydrogen for every 1 mole of hydrogen. So now you can see that we have the unit that we want, and if I have done this math correctly, I will get a value of 1.03 times 10 to the 24th atoms of hydrogen. So the important part of this reaction was to know how many hydrogens are in each one of my ureas. Other than that, this is going to be simple unit conversion. Our final example for this video, which was done in the fall of 2018 exam, we are going to do a fairly similar reaction to what we just did in the last example. How many ions of chloride are there in 0.230 moles of rhenium 6 chloride, which has a formula of ReCl6? So what we need to do is start with our moles of our original compound. So we have 0.230 moles of our ReCl6. So what can we do? Well, now we need to go and get the chlorine ratio. How many chlorines are there for each one of those? Well, we are going to get 6 moles of our Cl- for every 1 mole of our ReCl6. Then what we can do, because now we have moles of chlorine, is that we can take this value and multiply it by our Avogadro's number. So that is 6.022 times 10 to the 23rd ions of our chloride for every 1 mole of our chloride. So now we can get rid of our moles of rhenium chloride, we can get rid of our moles of chloride, and we are left with ions of chloride. If you go and do this math, you will come out to get an answer of 8.31 times 10 to the 23rd ions of our chloride. If we look at the left, you will see that that is answer E. In this video, you saw the importance of the mole, which we've talked about previously, Avogadro's number, and now using our molecular mass or our molar mass in order to start to calculate important values such as the number of atoms, the number of grams, as well as the number of moles. In future videos, you're going to be using this skill when you are starting to delve into the likes of stoichiometry. Have a great day.